Okay, this is learning target C11, my consult-related rates problems. Okay, this will be more along the lines of some more story problems, more applications of the derivative. Okay, I'm going to be doing a lot of examples from the textbook to kind of help you. I think they're good examples and they should relate quite well to some of your homework problems. Okay, I am on page 149. If you'd like to follow along right now. I'm going to start with a slightly different equation, all right, just to give you a little bit more of a visual aid. All right, let's say we have, God, put that away. Let's say we have a cylinder full of liquid, okay, and we put a hole in the bottom of it and the water starts to drain out. Okay? I would like to know how fast the volume of the water is changing with respect to time. Okay, how do we do this in the physics problem? There's some very similar stuff to it, yep. But there are some different things multiple things that could be changing at one time. They get a little bit tougher, but kind of the same idea. Okay, so to start with, I'd write down the formula for the volume. Because if I want to know how fast the volume is changing with respect to time, we would need to start with the volume formula. So if you have a true cylinder, pi r squared h, right? Okay? So I have, what's going on? Volume equals pi r squared h. And if you recall, I wanted to know how fast the volume was changing with respect to time. So actually, I want to find then dV over dt. dV over dt represents the change in volume with respect to time. How fast the volume is changing at a given instance in time, okay? We've been doing a lot of dy over dx, which is an instantaneous slope. How fast the y is changing with respect to x. Okay, y over x, rise over run. All right, but I want to know how fast the volume is changing with respect to time. So I need to differentiate both sides with respect to t. Well,
doesn't that depend on how big the hole is, essentially?
Okay. Oh, yeah, absolutely. Okay, there's got to be some given information to you, but I'm not giving you that there. I'm starting something else here. Okay? I need to differentiate both sides with respect to t, or time. Well, what do you notice? There is no time variable. There is no t variable. So I'm going to differentiate everything with respect to t. Well, if you think back, if I'm differentiating y with respect to x, what did you have to add every time you differentiated with a variable that's not the one that you're after?
Over dt.
You had to do that implicit differentiation, okay? So it'd be the same thing here. What is the derivative of the variable v? 1, but you're not differentiating with respect to v, so therefore after you find the derivative of v, which would be 1, you'd have to multiply that by dv dt. So really this becomes 1 dv dt. On the other side, you have a product there. I'm going to put the pi with the r squared, so essentially I'm going to have parentheses pi r squared is going to be my 1, and then h is going to be my 2, and I'm going to do the product rule. Okay, so pi r squared, there's my 1, times d2. What's the derivative of h with respect to t?
1 times dv over dt.
1 times, or not dv over dt, dh over dt. Okay? So 1 times dh over dt. So there's my 1 d2 plus my 2, and then what's going to be the derivative of pi r squared with respect to time?
2 pi r
2 pi r
dr
dt. Yep. I run out of room. 2 pi r times dr over dt. This expression right here represents how fast the volume is changing with respect to time. Obviously, there are a lot of variables here that we don't know as of right now. You'd have to be given some of that information. We could probably figure out the radius of the cylinder pretty easily. That would be given to you, so that takes care of that. You're probably going to be given the height as well, okay? Here's the radius again. dr dt, well, that one actually would probably end up being, if you're talking about how fast the radius of the water is changing with respect to time, if you are in a cylinder,
Well, it's not going to
it's
change.
not. So that part would probably end up well, it would become 0 in a cylinder, in the instance of a cylinder, okay? dr dt represents how fast the radius is changing with respect to time. The radius wouldn't be changing in a cylinder. If you are on page 149, they did it with a cone. That definitely would be changing. As the water drains out of a cone, the radius would definitely be shrinking as you go down, so that I'd have to tell you how fast the radius is changing with respect to time. And dh dt, you would have to figure out how fast the height of the water is changing with respect to time. It would have to be a constant value, and then you could plug that value in right there. And once you plug in all those variables, you can figure out how fast the volume is changing with respect to time.
I thought it wasn't a constant value when like the height of the water was like being released from the cylinder. Like wasn't that in the past problem and it like is faster when the beginning is over?
Or it might be at a given moment in time or something like that. But we would have to figure out exactly, the problems I'm going to give you are going to have specific values, so, but yeah, yes. All right, but I just wanted to show you a little bit how you find the derivative of a function with respect to a variable that's not even in the function. Okay? And the reason you're going to do that is because you want to find how fast something is changing, usually with respect to time. And I'm going to jump to page 150, and we're talking about, and this is a very common problem in calculus, the ripples in a pond. Okay, and you've seen a problem like this before. Okay, the ripples in a pond. So, here's our situation. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Concentric meaning they all have the same center. You know when you drop something in water, okay? The pond, there's waves that come out from there, okay, making just ripples in the water, going away from where the stone entered the water, okay? The radius of the outer ripple is increasing at a constant rate of 1 foot per second, okay? When they tell you the radius is increasing at a constant rate of 1 foot per second, they are giving you the value of dr dt. I know that dr dt is going to equal 1. Why do I know that? They're telling you the rate at which the radius is changing. So they've told me that dr dt is equal to 1, meaning the radius is increasing at a constant rate, or dr dt is always going to be 1 foot per second. Now it says when the radius is 4 feet, so in other words, when r equals 4, and you might want to write out some more of this problem potentially, okay? Pebble dropped into a pond problem. When the radius is 4, at what rate is the total area of the disturbed water changing? So in other words, what rate is the area of that circle changing? So when r equals 4, I want to know how fast the area of that circle is changing at that very instance. So in other words, I'm going to try and find the value of what variable? dA dt, okay? Mm-hmm. So in a nutshell, here is what the problem is telling us to do. This is basically all the important information you can gather from that story problem there that nobody's looking at on page 150, okay? Just might be easier if you saw it, but maybe not. Maybe I do a really good job.
150?
Yes, 150. So, we know how fast the radius is changing with respect to time. at the moment when that radius of that circle is equal to 4 feet, how fast is the area of that circle changing? How fast is the area of the circle of the ripple in the water changing? Well, what do you think you could do first? Write out the area formula of a circle. Yeah. So area equals pi r squared, correct?
Mm-hmm.
Okay. What am I trying to find?
Area with respect to time.
The change in area with respect to time, and that's represented by what? dA dt. So what should I do to my area formula that I have written here? Find the derivative with respect to time. So differentiate both sides with respect to time. What will I get? Well, just 1 what? 1 dA dt equals
2
pi r
dr over dt.
dr dt. Yep. 2 pi r times dr dt.
And since that's equal to 1, we just.
Now I can start plugging stuff in and I'm going to get my answer. Yep. Do I know what the radius is? 4, because that's where I'm interested. I'm interested at the moment the radius is 4, how fast is the area increasing? That was in the question, so 4 goes here. dr dt is 1, so 1 goes there. So 2 times pi times 4 times 1, and I get 8 pi, what? Label.
Squared.
Squared what? Feet squared
Per second.
per second. Yep, because it's an instantaneous rate of change. It's how fast the area is changing with respect to time. Okay, so this was in that was in seconds, correct? 1 foot per second. Okay, this was 1 foot per second. So therefore, feet squared per second. So at that very moment, when that radius of that circle got to 4 feet, the area of that circle is changing this quickly. Okay, that's the instantaneous rate of change of the area of the circle. Okay, 8 pi feet squared per second. Questions, thoughts? Okay.
Can it be square feet?
Yeah,
Okay.
square feet, feet squared.
I mean, the only reason I ask
Did I
is
say
just
feet?
because of how I visualize it for thinking. Never mind.
Okay.
Simply.
Alright, on the bottom of page 150, there are some guidelines to solving related rate problems. I've kind of talked you through some of that already. It says identify all the given quantities and the quantities to be determined. That's pretty much what I did. I read the situation and I wrote down the stuff I knew and I wrote down the stuff that I wanted to find out. That's going to be a very commonplace, okay? Make a sketch, label the quantities. Sketches can be important on some of them, some they maybe won't be. Number 2, write an equation involving the variables whose rates of change either are given or are to be determined. That's what we did. We started by writing the equation of what we wanted to find. Step 3, using the chain rule, implicitly differentiate both sides of the equation with respect to time. That's what we did next. We differentiated both sides with respect to time. And step 4, after completing step 3, substituted in the resulting equation all the known variables and solve for the required rate of change. So that's kind of your step-by-step procedure. We just did it. I don't know if it'll be beneficial to you to write those down. Entirely your call. Okay? Go over to page 151. We're going to blow up a balloon.
Sounds like fun. Can we do it?
Yeah, can actually,
I don't have any balloons, I'm sorry.
they have them down at the end.
Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. Let's identify everything we know and everything we're trying to figure out. What do you guys think? without really looking down. Try to not cheat.
We want volume of the sphere, or like the formula for that.
We will end up using the volume of the sphere formula. That's kind of step 2. I want to identify all the stuff that I know first.
Oh,
Write down the variables I know, write down the variables I'm trying to figure out.
well, you know, dv over dt.
dr dt is what we're trying to find out.
And then you know what dv over dt is.
We know dv dt because it says air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. That's how fast air is being moved into this balloon. That would be dv dt. That's telling you the amount of volume that's being put into this balloon. So dv dt equals 4.5 cubic feet per minute. Okay? What else do we know? The r, the radius is 2 feet. Big balloon. What are we trying to find?
When r
The rate of change of the radius. So what am I trying to find then? dr dt. Yep. dr dt is what I'm trying to figure out. Find how fast the radius is changing. At the moment that radius hits a radius of 2 feet, what is its instantaneous velocity? How fast is the radius changing in a sense, okay? How fast is the radius changing at that very instance it's reached a length of 2 feet, okay? So, I've written down the stuff that I know. I wrote down the stuff that I'm trying to solve for, trying to figure out. Now, let's go to the, what equation? Volume of a sphere. It said it was a spherical balloon. What is the volume formula for
Can
a
I just
sphere?
look at it?
4 pi r to the third.
4/3 pi r cubed. Pretty good. Okay, 4/3 pi r cubed. So volume equals 4/3 pi times the radius cubed.
I peeked in
Why
geometry.
is their given rate double?
What's that?
Why is their given rate 9?
Well, you're certainly not going higher now.
Ah, thanks, Luke. We're
9/2.
gonna have to do the fractions.
Why'd they
You're the
double?
one who said it.
Hmm?
Why'd they change theirs?
What do you mean?
Their given rate is 9/2, we just said 4.5.
That's
9/2 is 4.5.
Oh, duh.
That's all right. I don't really know why they
I mean,
did.
like, why'd they write it like that?
I don't know. That's a great question.
Is it because we have fractions in there?
Potentially, to solve it without a calculator later might be easier. But let's see. All right, what are we gonna do now? Derivative with respect to.
R, or not R.
dr.
We're gonna differentiate both sides with respect to t. Okay.
Yes.
We're differentiating both sides with respect to t because we're trying to find the change in the radius with respect to time. Trying to get you in the habit of, when you see this, understanding it means how fast is the radius changing with respect to how fast the time is changing. Okay? So we're going to differentiate both sides with respect to t. What do we get?
dv over dt
dv dt.
equals 4 pi r squared dr dt?
Good. 4 pi r squared times dr dt. You take 3 times 4/3, because that's your power rule. 3 times 4/3 gives you the number 4. And then it's pi times the radius, 1 less power, so it's squared. 4 pi r squared.
That's unfortunate.
Then we gotta divide by 4 pi r squared.
Yep, I'll show a little bit of work here. So 4.5 is this. 4 times pi times, I'm going to do 2 squared in my head. All right, 2 squared is 4. I don't know dr dt.
So you solve for dr dt.
Well, so if I want my answer in terms of pi, probably good to, that's probably why they used a fraction in a sense, okay? You guys can figure out how to do that without a fraction, I would think, on your calculator, but if not, it's fine. So I have 4.5 equals 16 pi dr dt. I'm going to divide both sides by 16 pi, or really multiply by 1 over 16 pi. Multiply by the reciprocal instead of dividing. So when I have 9 halves equals 16 pi dr dt, and I multiply by 1 over 16 pi, that would give me 9 over 32 pi equals dr dt.
That's why they did it.
Okay. Yeah, that's probably why they wrote it as a fraction, because that's a lot easier to do than think what's 4.5 divided by 16. Okay, but if you did 4.5 divided by 16, all right, you would get this fraction, 9 over 32. Put the pi down there on the bottom. Now, I guess to me though, that I'm going to show you that way, but I'm quite certain that I'm going to ask for a decimal answer, because when you're working in story problems, okay, me saying, oh, the radius is changing at 9 over 32 pi feet per minute. It doesn't tell me a whole heck of a lot. I'd rather have the decimal, all right, when you're working with story problems.
Including with the
Okay.
pi part of it, or do you want
No, never put a decimal with pi. If you leave pi in your answer, always leave it as a fraction. Okay? Never do like 3.7 pi. Okay? If you rounded something to 3.7 and then tacking a pi onto it, you just as well have multiplied it by pi and rounded the final answer in the end. Okay? According to the book, this looks like it's about 0.09 feet per minute. 0.09 feet per minute. Okay?
Very much.
So that tells me that my radius is changing at roughly 9/100ths of a foot per minute. Okay?
Person sucks at looking up the list.
Picture makes it look like it's a some sort of pump, but to be real skeptical on that, if you're actually using a hand pump, I find it hard to believe that the volume can be changing at a constant rate. But that's maybe a little.
Yes, but it's over a minute, so that's per minute. So if you pump it certain number of times per minute, then
But at the very
Not all pumps are created equal.
great. All right.
maybe it's an average.
Trying to decide if I want to do one more.
What a
It
lovely
might not hurt to
lobster.
do one more, and then I'll just give you
Sticker.
problems.
Test.
Okay.
Yeah, I want to know how I did on my test.
Let's go to example 4 on page 152. Be fairly challenging.
Yay.
An airplane is flying on a flight path that will take it directly over a radar tracking station as shown in the figure over there to the left. If S is decreasing at a rate of 400 miles per hour when S equals 10 miles, what is the speed of the plane?
So I like the picture there.
Okay.
So X is no, that's how close it's getting there. S is the hypotenuse.
I was,
Well, you should think about it in your head.
Okay.
Appreciate it.
I want a drawing of the
Yeah, there's no
Draw a
drawing.
plane.
It's 6
There's no
squared.
Draw a
drawing.
plane. No. Draw a plane.
Well, it's 36.
I'm not drawing a plane.
Draw a
I
plane.
can't draw a plane,
You
alright?
have to
Are we
draw
talking
a
about like
plane.
a plane,
I
like
can't do it.
I don't know
Whoa,
what
wait.
plane you're talking about.
But,
a geometry plane? You know?
6 squared
I'm so confused.
or
what we're talking
36 plus X squared equals S
Is that a
squared.
plane?
That's a kite.
Kite
That's
that's
a
flying
geometry
through the
plane.
sky.
You guys are so mean.
I
Alright,
can see
It's a
like
beautiful plane.
Okay,
It's a plane
so
plane.
here's our picture.
But
We
it's
got
a-
a plane flying this direction. Okay, here's our radar tower. It gave us that the plane is 6 miles above the radar tower, so that's where this came into play. That was given to us. Okay. Alright. S is decreasing at a rate of 400 miles per hour. So
Yes, DT.
ds dt, how fast s is changing with respect to time, because it said it's decreasing,
Negative?
negative 400 miles per hour. So ds dt equals negative 400 miles per hour. Okay? It says that's how fast it is decreasing at the moment when s is 10 miles. So that was given to us. S is 10 miles. Okay? And then what is the speed of the plane? Okay? What is the speed? In order to figure out the speed or how fast this plane is traveling, what will I need to find out?
Distance over time for x.
Dx dt.
Why are you using that?
Because that's,
Oh, because that's.
the plane is here and it's doing this, so we want to know how fast x is changing. If we can figure out how fast x is changing at that moment, you're figuring out the velocity of the plane. Keep in mind, based on this setup, I mean, we'll probably get a negative value, but because then we ask for speed, you can just make it positive.
So, would we want to start with 36 plus x squared equals s squared?
Well, it might be helpful to figure out what x is at the very moment we're interested in when s is 10.
Oh,
So.
At the very moment when s is 10, if this were 10 at this very instance,
100
what would
minus
x be?
100 minus 36 and take
8,
the square
so
root.
3, 4, 5. 3, 4, 5, 6, 8, 10. The 3, 4, 5 special right triangles. Right? Don't know that?
Yeah.
3 squared plus 4 squared equals 5 squared, right?
Yeah.
Okay, that's kind of one of the right triangles that always shows up in geometry. 3, 4, 5, if you make that ratio consistent, you still have right triangles. 3, 4, 5, 6, 8, 10, 9, 12, 15, 30, 40, 50, those are all right triangles, okay? But yeah, do Pythagorean theorem if you don't know that. So at that very moment, x is equal to 8, okay? So, now keep in mind, these are just at this very instance, all right? Those are changing. X is changing, S is changing. What formula, you know how we had the area formula or the volume formula, what formula do you think we'll probably use to start to write out and then plug in stuff that we know?
A squared plus b squared equals c squared.
Mm-hmm. The only thing we can really write to relate these things to one another would be Pythagorean's theorem.
And the
So
only
x
constant.
squared plus 6 squared equals s squared.
Yeah. And then would we want to do all of that to time?
I know we know all those, but that's not going to help us find this.
So now we do that to time?
We differentiate both sides with respect to time.
Okay. So that would be 2x.
X squared plus 6 squared will always equal s squared.
why it's S and not
At the when we go to plug stuff in, we'll plug in 10, but not until we do the derivative, because if we make these all constants, you know, if we make this 6, make this 8, make that 10, you're going to get 0 equals 0 when you do the derivative. And keep in mind, we're trying to find dx dt. S is changing, X is changing. We got to leave them as variables because they are changing. They're not staying constant. They're not staying. This isn't staying 8. That's not staying 10. But when we go to find this, we know at the very instant we're trying to find this, that is that much and that is that much. At the very instant we're trying to find how fast dx dt is changing. So 2x dx dt
Nothing,
plus 0
Yeah.
equals 2s ds dt.
Interesting.
Plug in what you know. So x at this very instance is 8. We don't know dx dt. So I got 16 dx dt.
Equals 2s times.
2 times 10 would be 20 times negative 400.
Yeah, we do know that.
S is 10, ds dt is negative 400. So 20 times negative 400, negative 8,000.
And then divide that by 16.
Divide that by 16,
400.
because we're solving for
500.
Oh, they're both two.
dx dt. So dx dt equals negative what? 500?
Bingo.
Okay.
So 500.
So that tells you that dx dt, at the very moment this gets to 10, the x value is changing at negative 500 miles per hour, but the question did ask, what is the speed?
Make it positive.
Make it positive, because speed is always positive, so my answer would be, that's how fast that plane is going at that given moment.
Sweet.
Okay?
That's not bad.
Alright, homework.
Oh my god.
We'll be working on these a little bit, but please do some on your own.
And we'll find it on the calendar. Do you want me to pause this? Oh wait, no, you
Which
probably
one?
want to show it.
All of it?
We will be doing all of these. I would ask for a goal for Monday, guys. Get those 4 done. Okay? These are the easy ones.
No, that was gonna be hard.
Alright?
Wait, which one's the easy one?
First one.
Pause
We're
it.
doing all of them, yes.